Greetings all. This screencast will wrap up the discussion of Chapter 15, Reaction Kinetics and Mechanisms, and it will be exclusively about mechanisms, Section 15.6. And of course, understanding the mechanism, the actual process or means by which the particles that make up my reactants become the particles which make up my products, is difficult to discern because obviously you can't look at it directly, at least not yet. But using some chemical intuition, using some common sense, using some logic, we can often gain an idea as to what that mechanism is likely to be and sort of deduce a mechanism that is consistent with what we know about reaction kinetic rates and consistent with what we know about particles colliding with each other in the collision theory. Remember, the particles that we're talking about might be molecules, they might be atoms, and they might be ions. So let's imagine that we have a chemical reaction that looks like this. We have some bromine gas that's going to combine with nitrogen monoxide in a 1:2 ratio to produce this compound right here. Now, we could say this might happen in one step, but in order for this to happen in one step, you would need one bromine molecule and two nitrogen monoxide molecules to strike each other at exactly the same time, with exactly the right orientations in space, with exactly the right amount of energy to produce the product. The likelihood of this, we would expect, is pretty slim. Just like in a traffic accident, sometimes a single car has an accident, crashing into a light post or something like that, and oftentimes two cars collide with each other. But very, very rarely do three cars all collide with each other at exactly the same time. And so we would anticipate that this is going to be a multi-step reaction, not a single step. So we might propose a two-step mechanism. Step number one would be where a bromine molecule collides with a nitrogen monoxide molecule and makes some intermediate product that looks like this. And then in a second step, that same unusual compound, Br2NO, strikes the other nitrogen monoxide molecule to produce this compound right here. And then when we combine the two steps, this will cancel out with this. We add up the reactants and we add up with the products, and we get the resulting mechanism that we had in the original balanced equation. Each one of these steps is called an elementary step. So we have one elementary step, we have the other elementary step, and that produces the overall reaction. And you might see that both of these steps only requires two molecules to collide with each other. This one and this one in the first step, this one and this one in the second step, and that is a much more likely scenario. Now, we have names for this, of course. If we have a single particle that is involved in a so-called collision, in other words, it decomposes, it breaks apart, whatever, we call that a unimolecular process, because uni means one. Right there. If we have two particles that collide with each other, like in the second step here, in this other example, That's a bimolecular process. 1, 2. This is what we mean by the molecularity of each elementary step. The molecularity in the first step is unimolecular. The molecularity in the second step is bimolecular. And the likelihood of there being a termolecular, where ter means 3, is pretty unlikely. You would have to have sufficient evidence to presume that you have a termolecular elementary step, requiring 3 particles to strike each other with the right amount of energy at the right time and at the right place and with the right orientation. That's what we mean by molecularity. Now, here is a very important point. We already know that when you write a rate equation, the coefficients in the balanced equation do not automatically become the exponents in the rate law. But when we talk about an elementary step, it is true that the coefficients in the balanced elementary step automatically become the exponents in the rate law expressing the rate of that elementary step. In other words, the stoichiometry becomes the exponents in the elementary step. But this is not true for the overall reaction. It's important to realize that for the rest of this discussion to make sense. So if we look at some examples of a unimolecular process, it would be, obviously, when your single reactant must be the only factor involved in the reaction rate and in the rate law. Obviously, this particle must somehow be either turning into an isomer of itself or decomposing. We can add several examples of bimolecular steps. Your 2 particles that collide might be different, or they might be the same. And a termolecular step would require 3 different particles, A plus B plus C, or 2A plus B, in order to generate that rate equation. And of course, those would be unlikely. Now you might say, what's the difference between the molecularity and the reaction order? Remember, the reaction order is the exponent in the rate law. And you can have the reaction order for each individual reactant in the rate law, and you can have the overall reaction order, which is the sum of the exponents in the rate law. And your molecularity and reaction order would be the same for each elementary step, but decidedly not the same for the overall reaction order. If we look at this example right here, here we have the hypochlorite ion decomposing into a chlorate and into 2 chlorides. And we would not expect this to be a one-step mechanism, because to be a one-step mechanism, you've got 3 hypochlorite ions, and this would be a termolecular process requiring all 3 hypochlorite ions to strike each other at the same time and strike each other with the right amount of energy and in the right orientation, and that would be pretty unlikely. So we would hypothesize or propose a multi-step mechanism, such as the one presented here in 2 steps. So we begin with one hypochlorite striking another hypochlorite to produce the chlorite ion and a chloride ion. And then my chlorite ion striking my other hypochlorite to produce my chlorate and my chloride. Now, obviously, I hope you think it's obvious, but you'll notice we have a reaction intermediate. My chlorite is produced in step 1. It is consumed in step 2, so that when I add up the reactants and products in both steps, it disappears. And let's come back here just to double check. It disappears, and you'll notice now that I have 2 chlorides, and I have 1 chlorate ion. So the 2 steps agrees with the overall balanced equation, and each step is bimolecular, and that makes a lot more sense. It would have a higher probability because bimolecular steps are much more common than termolecular steps. And let's come down here to now talk about reaction mechanism and rate equations. Let's suppose we want to build pizzas, make pizzas in an assembly line. And so we need somebody to take the shells out of the plastic package that we bought from another company and put that on a piece of cardboard. And then we need somebody else to put sauce, to label tomato sauce on the shell. And then we need somebody else to put cheese onto the sauce. Mozzarella, of course. We're not going to go with Emos here. And then we've got to put pepperoni on top of the pizza. And then, of course, after we bake it, we get to eat it. So let's suppose that Tommy is our person who's going to be taking the shell out of the plastic wrap from the other company and put it on a piece of cardboard or on a metal pizza tray for putting in the oven. And then Jordan is going to ladle the sauce onto the shell. Isabel is going to grab handfuls of cheese and sprinkle it all around. And then let's say Libby is going to put the pepperoni on top of the cheese. Now, Tommy's job is pretty easy, even for Tommy. And he can rip off that plastic and slap that shell onto the pizza tray. And Jordan, if you know Jordan, he's going to take a ladle, hopefully not use his cupped hand, and slobber that sauce all over the shell. And then Isabel, she's going to go in with her hands, hope maybe she's wearing a plastic glove or a latex glove, and she's going to sprinkle one big handful of mozzarella cheese. And she can do that pretty quickly as well. And then we come to pepperoni, but Libby, being the artistic one, very, very carefully puts the pepperoni pieces on the pizza. And it takes her a long time. Whereas Tommy can do 5 pizzas in a minute, and Jordan could do 6 pizzas in a minute, and Isabel could do 4 pizzas in a minute with the cheese. Libby can only do 2 pizzas a minute with her precision of placing the pepperoni just right on each pizza. How many pizzas do we get to eat a minute? And of course, the answer is based upon who's the slowest. The slow step in this reaction mechanism of making a pizza from its raw materials of shell and sauce and cheese and pepperoni is Libby. We only make 2 pizzas per minute. The process of putting pepperoni on the pizza by Libby is our rate determining step. Our rate determining step right there. That's as fast as we can go. So my rate law then has got to reflect the rate determining step. My rate law should be expressed in terms of the rate determining step, the reactants of the rate determining step. In this case, the pepperoni. So let's look at this example. Elementary step 1 combines A and B to produce 2 products, X and M. And then in elementary step 2, we have my reaction intermediate M also combining with A to produce some compound Y. And so when I add up the reactants and the products, my reaction intermediate produced in step 1 is consumed by step 2, and it doesn't show up in the overall reaction. 2A plus B produces X plus Y. You notice that overall this is termolecular, but we do not propose a termolecular step, elementary step, because that is very, very unlikely. So each of my elementary steps are bimolecular. Two particles must collide with each other. Now let's suppose that step 1 is very, very slow, and step 2 is very, very fast. Obviously, elementary step 1 dictates the rate of the reaction. So my rate law should be expressed in terms of the reactants in my slow step, A and B. And therefore, my rate law is going to equal some proportionality constant and the molarity of A times the molarity of B. That should make sense. Now, let's move on a little bit. And let's see if I can find that. Let's look at this example here with nitrogen dioxide and carbon monoxide. You'll notice that we propose 2 steps. And in these steps, we propose that my nitrogen dioxide molecules, 2 of them collide with each other to make nitrogen trioxide and nitrogen monoxide. And then in elementary step number 2, we propose that nitrogen trioxide, which is produced in step 1, is going to be consumed in step 2, and that species, that intermediate product, becomes my intermediate reactant. It reacts with carbon monoxide to produce nitrogen dioxide and carbon dioxide. Then we go ahead and we add up the reactants and we add up the products. My reactant intermediate doesn't show up, of course. And I have my overall reaction. Step 1 is slow. If I'm going to write my rate law, though, my rate law has to be based upon the slow step. And so my rate law is going to be based upon the molarity of my reactants, which are nitrogen dioxide, times some constant K. And since that is my elementary step, my coefficient becomes my exponent. But I also have, and that's the rate law, I should say, for the elementary step. But if I want my rate law for the overall reaction, it's going, pardon the unusual looking K's, it's kind of a tricky writing with this Apple pen. My rate law then is going to be based upon the nitrogen dioxide and on the carbon monoxide. So you can have rate laws for your elementary steps and your rate law for your overall reaction. Now finally, we have an unusual circumstance that occurs when what if my slow step contains a reaction intermediate? Consider this reaction right here. In this step 1, we're going to say that a single nitrogen monoxide collides with an oxygen molecule to make a reaction intermediate. And then my reaction intermediate collides with nitrogen monoxide to make my nitrogen dioxide. So that my reaction intermediate is produced in step 1 and is used up in step 2. Why are we proposing a 2-step mechanism? Because if you come back to the original reactants, that would require, if this were to be 1 step, that would require a termolecular process. That would require 2 nitrogen monoxides and one oxygen all to collide with each other at the same time with the right orientation and energy. A very, very unlikely scenario. And so we would propose 2 steps. Now, there's an important caveat here. If I'm going to write my rate law in terms of my slow step, the rate law should be written in terms of the slow step. My slow step has a reaction intermediate in it. And you're not allowed to write your rate law with a reaction intermediate in it. You should say, oh no, my rate law is going to have a reaction intermediate in it, and which in this case is oh no, O-O-N-O. So if I write my rate law right here in terms of the slow step, it's written in terms of this reaction intermediate, and that is verboten. So I need to figure out a way to get rid of oh no and express it in terms of the actual reactants. So here's what we do, and this is the tricky part and perhaps the hardest part in the entire chapter, and the one question on the test that is most frequently missed. And that is that what we're going to do is recognize, if we come back up here, that this slow step right here causes the first step to get backed up. This fast step is trying to go to the right. But it can't go to the right because the nitrogen, the OONO, doesn't get used up fast enough. And so it creates a backlog. The assembly line has too many of these waiting to be used up in step 2. And so with too many of these to be used up, we set up a situation where we have equilibrium, that some of my products revert back into my reactants. And so step 1 ends up being in equilibrium. Now, next chapter is all about equilibrium, so this is a bit of a preview. In equilibrium, the forward reaction and the reverse reaction occur at the same rate. And so my forward reaction and my reverse reaction mean I reach a situation where I have both reactants and products in my reaction container at the same time. And so what we're going to do, and this is a preview of next chapter, is that when we write what we call an equilibrium constant, we put the reactants, my forward reaction and my reverse reaction in the equation at the same time. In other words, I'm going to put my products of equilibrium and my reactants of equilibrium. We always put the products in the numerator and the reactants in the denominator for a reaction that's at equilibrium. So in that first step, my product is oh no, and the reactants are nitrogen monoxide and oxygen. So now when I write my rate law, we see that my rate law looks like this, where I have oh no as my reactant and my products, there's oh no, and here's my products, and of course there's my equilibrium constant. And what we're going to do is actually get that to cancel out. So here's my rate, and instead of NO, you'll notice that NO actually equals nitrogen monoxide and oxygen. They're the same. So instead of saying NO, I'm going to put this in its place. And then I'm going to combine all of my constants into one big grand constant. And now I have a rate law right here that is expressed in terms of my reactants, and it does not have the reaction intermediate, oh no, in it. And it's overall third order, 2 plus 1. It's overall third order, but we know it's not termolecular. And that's how you get rid of a reaction intermediate when you find it in the slow step. And again, our rate law right here cannot have the reaction intermediate in it, and it must be based on the slow step in the reaction mechanism.